Okay, so I sort of mentioned the beginning of my career was 40 years ago, and effectively I have spent most of those 40 years developing an irrigation scheduling model, which you will see the outcomes of it this morning. And it's one of those things about delivering science back into practice that this is pretty much, I'd love it to be 20,000 fields I've worked on, in my career. Isn't quite there. It will be there next year, and as long as growers are still surviving this year to take up the service. But it's all driven by making sure that we can improve irrigation efficiency, use what we've got, understand what climate change is actually doing in terms of our growing in conditions and what we need to respond. Now, when I came 7 years ago, I was taken away from a journalist by Ryan because he was worried about the person just trying to get a fix on public drinking water supplies and security and whatever. And suddenly it's changed now. There's linear moves. There were none here when I last visited, and or said the pivots rather. And the thing is now realising that without water, we're going to be struggling in terms of potato production, and that occurs. It's here on PEI. It's over in the Pacific Northwest, and it's happening in Europe. Spain has had a disastrous year. It's had drought and excessive rainfall, same with Portugal. So we need to be thinking about securing water supplies. So I talked all day yesterday, went into a bar and I picked up a cough. So please stay away from me. That's why I'm croaking like this in terms of it. So, right, so this is this is normally a half-day talk. And what we're really going to focus on is the first 4 points in there, but owing to where we are geographically in terms of the island, I know many of you are growing fresh potatoes, so the bottom part about quality control is really important. So common scab, and I've spent quite a lot of my career working on how irrigation management controls common scab and developing best practice for growers in the UK. So that would be good to also revisit that. And the bits in the middle about how we apply water and how we measure soil water content, really, rather than me presenting, should come from you as questions. So ask me the questions and then I can fill in the gaps where we're not going to be presenting. So this is a bit of a start whereby we've got a sandy loam field here, a loamy sand on part where we've got significant contours. It's not atypical of what you might be growing on here, in that how do we plant potatoes? What do we plant and where do we get water, and what type of water do we use in terms of application, what are our risks, and what we do is set the growers up with this and get them to think about it. Now bear in mind, you're a bunch of converts who know about irrigation, most of you. Many of the people I talk to, they're supply chain managers, they wouldn't have a clue about this. So we introduce this and then we go back right at the end of the talk and say, right, what you've learned, what would change? And it's amazing how much people have picked up and said, well, we wouldn't do this, but we'd do this. So that's a suggestion to us, and we won't return to it at this particular point. But the crucial thing is, we're trying to use irrigation efficiently. We have potatoes that we grow in plant pots, and I will come back and keep alluding to that system about a plant pot. But we want to maximise what we get as our free source of water. I've got small ears, but it's not holding on. I
think it's upside down.
There. Okay, that's better. Right. We want to maximise what we get as free resources. Free resources is what you get out of the soil and what comes down from the heavens as rainfall. So the first thing in doing that is, when does our crop need irrigating? And I've heard all sorts of things like, Canada Day, or the 1st of June, or whatever. That's just a calendar date. It varies every year. It's not about that. It's about crop demand, need for water. If we need water early, and it's going to compromise yield development, then we need to apply it. If we run out of water, so be it, the crop's going to get its best start by having the water. So we need to understand how much water the crop needs, and then basically answer a series of questions about when do we start applying, how much do we apply, and then when do we next do it, and how do we manage scab control, and what do we do at the end of the season, and so on. So the first thing is understanding how much water a plant will actually use. But not just a plant, a potato crop, because we don't grow plants, we grow communities of plants in fields. So we're talking about a field of potatoes here. We need to maximise two things. One is the quantity of water we get out of the soil. So we want to empty the bucket as much as we can before the plant comes under stress. But on hot days, we want to extract that water as rapidly as possible so that we can meet our evaporative demand of the crop canopy and the yield potential isn't lost. So it's not just about the amount of water, it's about how fast we can get it out on those hot days. Basically, if we have a rain-fed scenario, so I'll be doing this work in the Pacific Northwest, and it's an arid desert where rainfall doesn't interfere. Okay, where rainfall doesn't interfere, then it's pretty easy to schedule irrigation because you put the water on and there's nothing coming from the heavens. But where it does rain, and I'm using 2025 data from this side of the island for the scenario I'm going to run at the end of this talk, and basically it did rain quite a lot in 2025, but it was also extremely dry in other parts, and also it was very hot in those times. So we need to utilise our free source of water, the rainfall, as much as possible. And that's going to be the focus on how we do that in managing with deficit irrigation, how much we empty our potato bucket in the field. And then what we're also trying to do is maximise our tuber quality, and this is largely focused on not allowing common scab to come in potato packing varieties, but also avoiding the things associated with overwatering, things like powdery scab. If you've got inoculum in the field, then irrigating at crucial times will increase the chance of you getting that disease and disfiguring your tubers or eliminating them from the packing line. If we overwater, lenticel eruption, I'm sure you're familiar with that. Things get in through those lenticels, so bacteria and other fungi can get in. So there's a place for invasion of pathogens. And also, where we overwater, we affect the calcium supply by drowning the soil in water. We can actually affect internal defects and also processing quality. And ultimately, if we can do this, what we're trying to do is minimise our losses from irrigation. So if we can keep on putting water on, but if we keep getting drainage, then that's a waste of a very valuable resource, and that certainly applies over here because irrigation is just coming onto line, or it's costly, or your wells are of limited capacity. There were two equations that I put up. This is the second one. This is even more complicated. Okay, so I do not test any student on this, but basically what it is you've got two people combining here: Howard Penman, who was an agrometeorologist, and John Monteith, who was a crop physiologist, combining together to basically produce an equation that would calculate ET, evapotranspiration. Okay, lots of things being measured, lots of difficult calculations. When you run it through, you can get this online. You can type in Penman Monteith ETO and type it in, and you can put your own data in, and you can get a number out, which is the daily water use of the crop. Okay, so we can do that. But the key thing is what that all is. It relies on the three main components of how much water vapour we can get into that particular air around the leaves. Now I'm going to, because we've got a bit of time, what is the major function of the evapotranspiration moving through that plant? In which case here you've got a picture of a, more like a bean plant. What is the main function of water moving through that plant, up the stem, out to the leaves, and evaporating up into the sky? What's the main importance of that? What's the driver?
So, cooling.
Good, well done, Ryan. You've been listening for the last 2 days. It's quite, and I don't know. Please stick your hands up if you didn't know that. So you did know it, you just weren't willing to say it. Okay, there's a difference there. So the main reason is, on a 13-degree, dull, Scottish, hard day, when it barely gets light, then basically the plant doesn't need to keep cool. As you raise ambient temperature, the leaf surface being green absorbs more energy and will be a higher temperature than ambient temperature. Okay, so that's the first thing. Because the leaves are green, if the leaves were black, they'd be even higher temperature, but they're generally dark green, so they have a higher temperature. As we raise up our ambient temperature, let's make it to 25 degrees, our leaf temperature is higher than ambient. Our leaves now are sort of 27, 28 degrees. If we push that temperature up to 30 degrees, suddenly our leaf temperature can be 34, 35 degrees. At that particular stage, then the plant is beginning to respire very rapidly. So bear in mind that respiration rates for every 10-degree rise in temperature double. So we've gone from, let's call it 10, 20, now 30. What we're doing is the leaves are respiring carbohydrate, as in material that you want, rather than putting it to the tubers. So as temperatures go up, the plant is losing efficiency. There's lots of energy to capture and drive yield, but now the plant is losing potential yield because it's just carbohydrate to live. So that's the first thing, why potatoes is an optimum temperature for potatoes. Not that potatoes won't grow above 25 degrees, but it's an optimum temperature, somewhere between 20 and 30 degrees. When you balance out basically the energy input, so higher energy means more yield, because energy drives carbohydrate production from capture of CO2, converting it through the solar system into sugars that go to make starch. But when you start getting to 30, it might be a very bright day, but the plant now is starting to lose some of the stuff you've built into it during the day. So there's an optimal window. But the key thing all about that is the leaves will function perfectly happily for yield as long as they're well supplied with water. If you drought this crop, and we have 20 degrees Celsius ambient temperature, then the leaf surface temperature will be more like 26 or 27, so we're now 6 or 7 degrees warmer. Now, make it 30 degrees, and the plant is under stress. We're now at the high 30 end. That's the sort of temperature, if you ever, sous vide salmon or chicken or boiled an egg, 40 degrees is the point when you start getting enzyme denaturation. In other words, what you're doing is you're boiling enzymes. And that's when you start to see senescence. The plant then is trying to heal itself from damage. So the crucial thing is avoiding those leaves getting to high 30 temperature. People keep saying 30 degrees potatoes don't grow. They do grow, otherwise the Pacific Northwest would be in a completely different situation to where they are now. Okay, they do grow. The key is maintaining water flow through that plant. So the key component of a plant moving water is to keep cool, but the cooling function really only comes in when we're talking about 23, 24, 25 Celsius temperature as ambient temperature, so what you see as a weather forecast. That's when we start to need to maintain that water flow, because if we don't allow that plant to have adequate water, it will slow down its breathing, it will close those stomata, which are exchanging CO2 to produce your yield. It will slow them down by trying to restrict and protect its water supply. At that point, as soon as those breathing pores are closed or partially closed, evaporation slows down very dramatically, temperature of leaves goes up. So what we're trying to do is on hot afternoon days is to keep those stomata open as much as possible. And that's all about deficit irrigation, is how wet do we need to keep the soil before we avoid stomatal closure, and therefore what we're losing is potential yield. So this is all about that. Evapotranspiration is about cooling function, but the cooling really only kicks in probably in mid-20s in terms of that temperature. That's when the plant needs to lower its temperature, otherwise it will get too hot. So that the energy drives evaporation. Air temperature, the warmer the air, it's a bit like the opposite of a store. Air temperature, the warmer the air, the more water vapour it holds. The colder the air, the more it drops out, so you'll get dew point at very cold temperatures. So air temperature is important. Lots of energy evaporates water. It gets absorbed by the air. The warmer the air, the more water vapour. The opposite applies to relative humidity. If air is relatively humid as it moves across this plant, it can't absorb much water. But if it's very, very arid, so maybe 20 or 30% humidity, it can pick up a lot of water vapour. And the key thing then is it will sit around the plant. If we can move those trucks of moist air away by having higher wind speed, then we end up with higher evapotranspiration. So the key things are energy, temperature, relative humidity, and the speed at which wind goes past those leaves. That's a simple process. That complicated equation is nothing more than that. Now, because energy, drives evapotranspiration, so increasing radiation. This is a very bright PEI day in the middle of July, up at the 30 megajoules per metre squared. And the evaporation rate you can see there would be up, in this sort of territory, would be up into nearly 6 millimetres per day. I'm going to show you an example from 2025 where your ET rate did actually exceed 6 millimetres on one day, in the middle of August. So I'm going to show you that example. But the key thing there is more radiation means more evaporation. So that's the first thing. And because evaporation is determined by radiation, but irradiation also drives yield. So capture more radiation means you get more carbohydrate. Therefore, the next stage is transpiration through the plant actually is directly related to tuber fresh weight yield, the bit you sell. Okay? So I say at this point, because it comes back to haunt students at the end, when they basically say, okay, I need you to tell me how much water does it take to grow a 60-ton crop? Okay? Now this isn't how much irrigation and rainfall, it's the amount of water the plant actually needs to use to produce that 60 tonnes. So if you draw a line up from 300 across to 60, it takes about 12 inches of water to go through that plant to produce 60 tonnes. So we're now in the sort of 500, 550 hundredweights per acre, and we're using 12 inches of water to go through the plant to do that. Okay? So that slope of that line is something I'm just going to come to next, which is water use efficiency is not the same as irrigation use efficiency. The slope of that line is basically mixing lots of units, 6 tonnes per hectare of fresh weight yield, every inch of water, 25 millimetres, applied to that particular field. Okay? If we look at irrigation responses, the best irrigation responses we see are about 90%. So this grower here was about 90% efficient in applying their water and getting the yield from that. 90% would be utopia. And you'll see in a moment where it's a lot lower than that. But there's another point here when we got a negative yield response, in other words, the yield went down when we applied water. What do you think might have happened there? Why have we got a yield going down when we've applied water? There's a couple of things that might have happened. So we've either watered the soil when it didn't need it and we drowned it, or we watered it and then we got a big dose of rainfall the next day. So effectively what we've done is put water on and it can't be used. If it's had an effect in terms of drowning the soil, removing the oxygen, we might lower the yield because the plant's actually anaerobic. So the range is there. The next slide really shows, okay, 90% would be brilliant, but we can get 100%. So this is basically some reference crop data with 2 varieties. Site in Cambridge, and this is the response of watering to yield. So it's not basically, it's the difference between unirrigated and irrigated, fully irrigated crops. There's a dotted line, which is effectively the slope of that graph 2 previous slides before. It's that 6 tonnes per hectare for every 25 millimetres of water use. And we've got 1 point at the top, 1, 2, 3, 4 points, very, very close to that line. So we can be pretty close to 100% efficiency. Sadly, the average is somewhere, that red line, excuse me, is actually about 55% efficient. That means 45% of our water is being wasted. What I'd like to do is improve overall efficiency for growers to put it somewhere between the dotted line and the red line. If we can get above 75%, then we can actually really utilise water efficiently. We're never going to get to 100%, except under very exceptional circumstances. But in rain-fed scenarios, we've always got the chance of saying, okay, what will happen tomorrow? Is it going to rain tomorrow? Should we delay irrigation to wait for the rain, or should we not? That's about scheduling and making your response in terms of that. So the key thing is we're not very good, and we need to improve. So potatoes both are responsive to irrigation, but they're also drought sensitive. Now, you can have a potato variety that's very, very drought resistant, but it often doesn't produce any yield. And we don't sell, potato plant above ground. We sell biological yield below ground, the tubers. So what we're really interested in here is how much water does it take to get a given increase in yield. And so the two are linked, but the most important things are potatoes are different to many other crops in that they have a low below ground conductance of water. 2 things happen there. First thing is they produce good rooting systems. So if we look at a couple of slides, this is a very good rooting system here on the bottom picture. It's actually 4 feet deep by 5 feet wide. It's pretty homogeneous. There's lots of density in the surface layer where all the nutrients and the water are largely distributed. The top picture could be basically a picture earlier in the season than that one, it actually is. Or it could be, as I'm about to say, that soil is compacted and every root has grown slower, so we've reduced the volume of roots by compacting the soil. So if I go back to this particular slide here, one of the reasons potatoes are bad Where we get the poor soil conditions is they're very, very sensitive to compaction, and so we can get very big rooting systems where we have very loose, uncompacted soil, but typically they're only about half that, and in many cases where we get compaction from cultivation machinery, rotary equipment, working in the soil in the wrong conditions in spring, we can end up with only about a fifth or a quarter of the roots production. So that's the key thing. Under good conditions, potatoes are pretty profuse rooting, but actually when we start to grow them naturally in our environments where we have wet springs, we reduce their root system overall size. The other thing is, and this is another exercise that we do, we give 4 or 5 people in the room a glass of water. We give 5 people different sizes of straws. One of them, would be a 15mm sort of bucket straw. We give people normal straws, finer straws, and the poor person who looks the biggest and you think would be able to suck the hardest gets given the pipette with a 0.5mm diameter. And the person with the pipette is still sucking, 3 hours later, trying to empty the glass of water. Potatoes are nearer the pipette end. In other words, they don't have the diameter of plumbing. So no matter how much suction you create through evapotranspiration, they just can't deliver it. So that's the real key thing. Restricted rooting, and those roots really don't have very big diameter plumbing to allow to do it. So we need to combine those things and say, why are potatoes, why are they responsive? It's because of these components matched with the demand of the crop. So I'm going to just go through this one. Potato roots basically differ between varieties in terms of their overall depth and density, the amount of roots they produce, because different varieties with different season lengths root for longer or shorter. So Cara, it's a very long season variety. It's still one of the top 2 varieties I've known globally that continues to root, in this case, right through to the end of August. It will continue to September and October if we let it, but it continues to produce roots right down to, in this case, nearly a metre. And then Atlantic, which would be a crop that some of you who grew chipping contracts would be aware of in PEI, is basically only 60 centimetres because it roots for shorter periods of time. So we can look at that. So what we get is pictures of roots like this, and then we start to convert this into water abstraction. So if you look at that picture on the bottom right-hand side, and then look at this graph, it's pretty similar. What it means is that the top quarter of that depth of rooting system, so the top 30 centimetres of that soil in the previous root diagram, 40% of the water uptake occurs in that zone. The next 25% down, 30% occurs. The last bottom 25% has about 10%. And the reason those bottom roots are really important is on hot days, they are the buffers. It's a long way to get to the surface there. It's nearly a metre in some cases. The plant will only tap into those roots when it really, really needs it. So if we start to see water uptake at 50, 60 centimetres, already our plant is under stress, and we can do something about it. We can start irrigating, or we can do some other processes to allow that to happen. But the bottom roots are the buffers on hot days, and they're the things that keep the plant growing and stop its leaf temperature going up. Okay, so what we've got here is, I'm going to come back to this, is we have plants that increase in size, and below ground they're also increasing in volume. So this is basically a 3-gallon bucket, and it's just decreasing in size as I've scaled the image. So what we've got there is the bucket goes from initially nothing. Potatoes are planted with no roots. They grow roots, it gets bigger and bigger. So the bucket gets bigger, and eventually it reaches this point, and then when that plant starts dying, eventually it goes back the other way. So we get maximum rooting depth, roots die, and eventually there's no depth, and we end up with a very, very small bucket when the crop is completely dead. So it goes this way, then back again. Okay, but we can also put different things in this bucket. We can put sand, peat, clay, sandy loam, your most common soil. So does it matter? It's bucket size times what's in it. Then we're going to make it more complicated than that in a moment. Now, you grow on a soil that is in the bottom left-hand corner of that diagram. Most of your soils, Ryan's informed me, are sandy loam soils. Maximum clay content would be around about 18%. Most of them would be in the sort of 12 to 14%. So you're on the sandy end of that textural triangle. This is actually a UK one. It's not a USDA one, which would have loam in the middle. But you've got sandy soils, silty soils, and a clay soil. Now, the key thing about this is that clay holds a lot of water. I'm sure we're aware of it. It's a heavy soil. It holds a lot of water. But does that mean it gives up its water to potatoes? The answer is no. So this is a complicated diagram. but I'm going to explain it by saying the soil at field capacity, FC, is a soil that is drained against gravity. Your fields are still draining at the moment because there's lots of water, snow melt on, but once that water has basically finished draining through the profile, our soils will hold no more water against gravity. That's our full point of field capacity. The permanent wilting point basically is the point when, if we didn't water, the plant would die. It's related to a scale called suction, so the higher up the scale, the greater the suction, and sunflowers or maize plants can extract water by sucking hard enough down to about 15 bars. So it's a logarithmic scale, so that permanent wilting point is 15 bars of soil tension. Potatoes can't suck that hard, so effectively they can only deliver water about the 7 to 9 bars of water potential, but this is a standard graph that most people understand in terms of permanent wilting point being 15 bars. So I'll explain it. Coarse sandy soils only hold about 9–10% water when they're full. We exhaust them with water, plant sucks the water out, and we get a soil that holds around about 1–1.5%. The difference between field capacity and plant depth is 8%. We move to the other end, a clay soil holds nearly 50% of water when it's full, but when the plant comes under stress in terms of it stops growing, we basically now have only got 34% water. Difference between full capacity of 50, 34% is 14%. So clay might hold a lot of water, but it's not very easily available to potatoes. The bit in the middle, so the fine sandy silt loams, which got a range of pore spaces that plants can suck out of, and potato plants can actually suck out really easily, is when you look at it, the difference between field capacity and permanent wilting point is now 23%. So the most water retentive soil in our bucket would be a sandy loam somewhere in the middle. Coarse sand gives up all its water very quickly, a clay soil gives its water up initially very, very quickly and then slowly tail. A soil that's clay, your potato plant would live a lot longer than a sandy soil. But it's not about living longer. We want to make sure this crop produces an economic yield, so we need to be aiming for allowing our plants to suck out water to ensure we utilise this maximum capacity of the soil. So there's the bucket size. If we look at that and we take not a coarse sand but a medium sand, the easily available water before the plant comes under stress, under an average PEI summer day in end of June, July and August, would be about 33 millimetres of water. We take our heavier soil, the fine sandy silt loam or silt loam, it basically holds another 22 millimetres more water. Right, remember I asked you a question, somebody's going to give me the answer, is how much water needs to go through the plant if you're growing 60 tonnes? What was the number I told you? 60 tonnes takes how many millimetres of water? 12 inches. Yeah, 12 inches, 300 millimetres. So 300 millimetres, and your bucket size and pot fill is only 22 millimetres. Most of the other amount of water that we need to go through the plant must come from rainfall and irrigation. So people talk a great deal about soil, but it's only about a tenth or a seventh of actually what we need to grow the crop. So soil type is important, but it's not as important as understanding where we're going to need to top that water supply up from rainfall. Right, okay. It gets a bit more complicated because it's not about a bucket getting bigger and the fact you've got sandy loam or a silt loam or a peat into it. What happens day by day affects how much suction the plant needs to create to extract water. So it was all done on soil water tension, suction. I've converted it into a millimetre deficit, so a deficit scenario whereby we can start to think about 40 millimetres of water disappearing from the soil, and actually that equates to something you can imagine. If you're going to irrigate and you've got a soil that's got a 25 millimetre deficit, your bucket is emptied with 25 mils of water, and you put 25 mils of rainfall or irrigation on, it should go back to field capacity. That's really easy to imagine, and it's sort of a simple approach. So I've worked on this, I worked on this for the middle part of my career. And what it shows is that, again, Howard Penman appears here, that the ratio between what the plant is actually using, so actual evapotranspiration, and what the plant would like to use if it was unrestricted in terms of its water supply, that's potential evapotranspiration, is all fine for a period. So the ratio is 1. So AE matches potential. We get to a point and then it starts to drop down at 80mm SMD, there's no more water use, this is the point of no return, plants stop growing. So what we want to do is define that as the point of limiting SMD when we're getting a loss of water use, and potentially that's a loss of yield. So that's really good. However, it's more dynamic than that, so that's a theory. What actually happens is that if we go to a really, really dull PEI day, when it's overcast, it's possibly never see the sun in terms of through the clouds, 100% cloud cover, we might be in the 1 to 2mm evaporation rate. As we move through here, and I mentioned in 2025 we had 1 day over 6mm, it is increasing rate of evapotranspiration per day, millimetres per day. So what you see is as we go from basically a soil that's under very, very low demand, dull days, it gets brighter, we move to 2 to 3mm, it gets to an average amount, 3 to 4mm, it goes to the green. As we move to 4 to 5, it moves leftwards. It means that the soil actually only functions at potential when it's wetter. Okay, so the direction is, with a very, very low demand day, we could extract about 70mm out of that bucket before our plant comes under stress and we lose yield. But on a hot day, so 4 to 5mm, it's sort of around about 27mm. The key thing is when we start going even hotter, and we're now your peak days of 6 or 7, two things happen. First thing is that basically the line moves even further to the left, so we're now looking at deficits less than 20mm before the plant, maintaining soil moisture deficits less than 20mm, otherwise the plant's going to come under stress. But already, at very high rates, we are not using the potential. So on hot days, the plant just can't suck fast enough. And this is all the whole process about balanced irrigation, that it's not just what happens over the whole season, it's about what actually happens on a day-to-day basis. You can have a cool day and then a very hot day, and the amount in the water available to the plant in the soil will change. Even though effectively nothing's changed overnight, there will be a difference in suction.
Just, can you define soil moisture deficit there for me?
Yeah. Right, there we go. So this is a bit further on. Okay, it's a balance, and it's a balance between incomings and outgoings. So the incomings are obviously rainfall, irrigation if you've got it. If you're at the bottom of a slope and your neighbour's irrigating, or it rains and you get run on, that's a benefit to water. And capillary rise would be a water table or a subsoil that can deliver water by capillary rise up the table. That's balanced by outgoings, which would be evapotranspiration or loss through the plant. Drainage, so that vertical movement through the soil down into the drains or into the substrata. And runoff, which is effectively when you irrigate, it runs down the end of the field and you can't gain it. So that's the key balance. If field capacity is the starting point, a zero deficit, then if we use 20mm of water through evapotranspiration, then we have a 20mm deficit. So the bucket is now 20mm short of water. Okay, if we do that for another 5 days, the bucket now has got 20 plus another 20 is now 40mm deficit. In theory, if we applied 40mm of water either as rainfall or irrigation, the bucket fills up. So just imagine a bucket, it's emptying the bucket and then refilling it. What happens if we overfill it? Then it flows over the top or it pushes out the bottom, then that's drainage loss. Okay, so it's a simple deficit saying that field capacity is as much water as your soil will hold against gravity, and all we're doing is drying that soil out. So when I talk about an 18mm deficit, I mean basically 3 days of water use at 6mm per day will drive that 18mm deficit. Does that make sense? So it's a bucket with a depth of water that you've dried out through evapotranspiration, and all you're trying to do is top it up or bring it up to a certain level. Okay, is that clear? Because that's very crucial. Okay, right. So we can then go back. And it comes down to this one here, which I think Ryan and I were talking about this, is basically Russet Burbank, the yield increases with the amount of water that we put through the plant. But can we gain any advantage in some varieties like this pattern, whereby as we get more water use, there's more water availability to the plant, it produces more leaves, more canopy, and actually doesn't produce any more tubers. Sadly, this variety doesn't have many cousins in terms of water use efficiency. So, in general, the more water we use, the more fresh weight yield we will get. And so to grow the sort of yield you see on top of here, it's just going to take more water going through the plant. There isn't that subtle change in efficiency that we see in this particular variety. So irrigation scheduling is about when to apply. At what point has our bucket emptied far enough to start to get a loss in potential water use and therefore a potential yield loss? Next one is how much do we apply? And B part 2 would be how much do we apply and when do we next go round? In other words, if you're using 3 millimetres per day, you're applying 15 millimetres, it will be every 5 days. If you're using 6 millimetres per day and you're applying 12 millimetres of water, it would be every 2 days. And I'll show you how that reflects in terms of scheduling. And then how do we apply it uniformly? We're not going to really cover that, but we could, maybe a question or something about whether boom irrigation is better than gun irrigation or drip or whatever. But it's about when to apply, how much to apply, when next to do it. So we've done that one. We don't need this one. Right, so this applies pretty much, PEI might be 45 degrees latitude and we're 52, but it's not that dissimilar to what we have on a hot summer in the UK. It's about the same as it is here. Obviously your days are much shorter, it's more intense, the radiation, but typically a potato crop with full crop canopy would be using about 3.3 millimetres per day. That equates to about 23 millimetres per week, or about an inch a week if we allow for a bit of evaporation loss during irrigation. The maximum measured water use, I need to change this, I should keep saying I should change it. In 2022, we basically measured 7.1 millimetres in the UK on an extremely hot day. And in the USA, lysimeter work done in Wisconsin did show that they could do 9 millimetres per day on one day. The next day it was 7, the following day it was 5 millimetres, but we actually measured water use up to 9 millimetres. Okay, so, the future is climate change is going to affect us. What will the future look like? So the future is 2050. Sadly, 2050 is more like 2040 now. We're moving faster than we predicted 20 years ago. So we're going to have a warmer growing season. The growing season will be lengthened by 5 to 6 weeks at both ends. Beginning, you'll be at the plant earlier, and you'll have full temperatures that are much warmer. Earlier planting will be allowed, more rapid emergence from higher soil temperatures, ground cover expansion initially because of temperature, higher temperature will be rapid. The determinant varieties, the short season varieties will just select earlier. They'll do their yield over a shorter period of time, and our longer season varieties that we might struggle to get to complete canopy maturity or tuber maturity will grow faster. So they'll be more mature at the same point in the season. There'll be longer spells of drought. There'll be more extreme rainfall events. We just used 341 millimetres per day on one event in northwestern England. Just to do that. So what does that mean for you guys? This is where we start to think about what PEI might need in terms of irrigation capacities. Basically, if we look at the pre-1990 scenarios versus our high emission scenarios, which is the upper end of our scale, and sadly we are moving towards that, is there'll be less cloud cover, more solar radiation, more ET energy. There'll be a 15 to 20% increase in evaporation during the season, and therefore an increased demand for irrigation. Question mark, will there? But CO2 has been forecast to rise from 350 parts per million in 1990 up to 550. We're well on that scale already. We've exceeded the chance of reaching 550 parts per million by probably 7 or 8 years. What that does is basically mean an increased growth rate, because tubers are working with plants are working with a richer fuel. There's more CO2. CO2 is the fuel that's catalysed by enzymes in the plant, utilising sunlight to grow carbohydrate, sugars, sucrose, effectively. So the plants will go faster. Because there's more CO2 in the atmosphere, the breathing pores won't need to be as widely open. They will close. That breathing pore then closes, means that we increase our water use efficiency of the plant because it doesn't evaporate as much. But it's going to be warmer, so the plant will need to cool. So ultimately, what we find is we might need another 1 or 2 irrigations, depends on how big they are. But basically, what we're going to do is have to use it over a shorter period of time, and we're going to have to think about the daily amount we apply rather than what we apply once a week. So this is a sort of summary. Can we manage? This is for the UK. Can we manage on existing resources? No. More unirrigated growers will need to think about irrigation or get out of business. think 4.5 mils per day, not 3.5. We'll need slightly more water, but we'll need it earlier and a very much increased rate of abstraction. Crops will just grow faster. And there's a problem with licensing, so we chatted about this the last 2 evenings about boreholes. You're in the same boat as we are. Trying to abstract water from a new borehole next to a residential development, you know, means we have to either go deeper or we have to fight for water. That was the issue, well, 9 years ago when I came, was, you know, we'll lose water for public drinking water supply. That's happening. You don't have a power station, but you have a domestic consumption that's really important. I don't know whether you've got many data centres, they need cooling as well, but irrigation in the UK only abstracts about 0.5% of the total volume abstracted. So it's not a big player. You've got definitely a bigger role because there's more agricultural involvement in PEI. But if you don't use it, then you'll lose it. If you don't use your licence, then basically that means they'll take it away from you. So we'll need more application capacity. So now the scheduling comes out. Here's a description of what the next 4 graphs mean. And what it basically says is that potential evapotranspiration is the water use by the crop given unlimited water supply. It's not too wet, but it's certainly not too dry. There's adequate water to maximise the growth rate on any one day. Actual evapotranspiration is what you guys do when you schedule irrigation with a less than perfect scenario. Okay? Soil moisture deficit is SMD, and the SMD descriptors are limiting SMD is when the crop water use slows below the potential rate because the soil is too dry to maintain that amount of water. Critical SMD don't want to be anywhere near that because that's the point when if you don't irrigate, the crop dies the next day. Okay, so we don't. Allowable SMD is, okay, if it takes us 7 days to irrigate the field, and we need to finish the last part of the field in 7 days' time, but we need to make sure it doesn't exceed the limiting SMD, we're going to have to start earlier when the soil is wetter to ensure that happens. So allowable is your management factor to say, how do we stop the limiting SMD being exceeded when we leave the field having finished irrigating? Scab SMD, we will cover this, we did it in the last 2 days. It's about the maximum permissible soil moisture deficit, not in the root zone, but where the tubers are, because that prevents the common scab infection. We can discuss how that does. Irrigation is not what we squirt up in the air, it's the amount hitting the crop canopy. And drainage is the loss below the rooting system. So you're going to start going here, and I will convert this 100 tonne per hectare. You know, you can do the conversions into that. We're talking of 900 hundredweights per hectare here. And it's just to show you it can be done. This was a 3.6 hectare field of Elland. It's a dual purpose, like Mountain Gem, dual purpose variety, can be used for French fries and making into, you know, oven chips. But it can also be used by the packing market increasingly. And what we've tried to show here is in 2024 we had a remarkably good season for growth. It was neither too hot nor too dry. It rained reasonably well in the middle of the season, which I'm going to explain, but we did need to practice late season irrigation. Ultimately, this crop delivered almost its potential yield. So there's 3 graphs, I'll explain what it is. First thing is, you've got canopy growth curve in green. So by the time the crop was defoliated on the 28th of September, it still had 85% ground cover. It developed really rapidly, so the rate of increase of that ground cover curve was 5–6% per day, which is about as fast as it gets. And the black line is our soil moisture deficit in our bucket of soil that we've got. These are sandy, these are loamy sand soils, so they're in that sandy end. And our bucket basically holds about 40 millimetres of water, 35 millimetres of water on an average day. Now, what we've got here is, the black line shows the soil moisture deficit in the bucket. The red line shows the do not exceed limiting SMD. So if you look at it, there's a day basically on the 28th of June when the red line drops down to 18 millimetres. That was an extremely hot 33-degree day. It was windy and it was dry, and so our bucket at that particular time could only be allowed to be emptied by 18 millimetres before the plant came under stress. If you go 2 weeks later, suddenly you see the red line is up above the 40 millimetres. It was a cool, dull period. We're not irrigating, we've got drainage. That's just because there's cloud and rain coming in. So we've now got the ability, we haven't changed much in the bucket in terms of soil type. The bucket's got bigger because our root system's got bigger, but now we could afford to allow that crop to dry out more before we irrigate it. So hence, we put an irrigation on the 28th of June, and then basically we ended up with 1, 2, 3, 4, 5, 6 irrigations going on during end of July through to end of August. And that basically managed to keep the black line below the red line. And then the black line started to increase at the end, and we decided that we weren't going to irrigate anymore because we'd got enough yield already at that particular stage. So what the bottom left-hand graph shows is basically the blue line is what the crop would have liked to have used if it had been adequately supplied with water for every single day of the season, and the green line is what the crop actually used according to that schedule. And there's only really, 3 days. There's that day at the end of June, and there's a couple of days at the end of July, and then mid-August. And what that does is the difference between the green and the blue lines is your yield loss. So if we plot yield loss on this graph, what we find is where these two lines, so there's the potential yield, which is the blue line, and the green line, which is the actual yield, they start to deviate at the end of June, where we end up with a bit of stress. They stay parallel with one another, and then at the end of the season, when we start to get the black line crossing the red line again, we end up losing yield. So the potential yield here was actually 107 tonnes, and we delivered and sold 101.7 tonnes to McCain's in the UK.
So how are you calculating the limiting soil moisture deficit?
Right. The calculation is based on the soil type in the bucket, the size of the bucket. So where this plant, where the green line comes down to on the axis somewhere around about 20-something of May, that's the point when the plant emerges. At that point, the bucket has no roots. Okay? So the plant is starting to grow. As that root system grows, the bucket gets bigger because we've got more roots. The soil type hasn't changed, it's still a loamy sand in it. So as we increase, we're getting more water availability in that pot because the root system's taking water out of a bigger zone. Okay? What we're then doing is saying, superimposing on that, basically, and I can, if you want to, I can give you the papers, it imposes the evapotranspiration demand and says, right, if it was an average day, then we can take 40 millimetres out, but if it's a hot day, we can only take 20 millimetres out, and if it's a really, really cool day, we can take 60. So it's a dynamic approach, we calculate that, and that's what this model I'm about to show you does. It works out how much water we need in the bucket to make sure it grows at the potential rate. And if you don't supply that water, because you're behind on the irrigation regime, it will lower the water use of the crop, so the green line will drop, and our yield loss will occur. So it's a calculation based on size of the bucket, what's in the bucket, and how hot it is that particular day. And not surprisingly, our weather goes up and down. We can have a cool day preceded by a hot day, and then another hot day afterwards, or vice versa. So it will go up and down. It's dynamic. On a cool day, the bucket doesn't need to be as full, and on a hot day, it needs to be significantly full of water. Okay. Right, and then if you get it wrong, then this is basically our drought season 25, so mimicking yours. This was a crop of Rusty Burbank, all doing fairly fine up to the point of getting to the end of, middle of August rather, and then the reservoir emptied. And we had no more water, other than a ½ inch of water to go back and put on immediately ahead of harvesting, to basically allow the soil to wet up. It's a sandy soil, this is a sand soil, wet up and allow some soil coverage up onto the primary web. So we put an irrigation event on. This was due to be going on basically on the 28th of September, never went on because it actually rained. So we managed to get out of that particular hole. But in this case, we didn't have enough irrigations to keep going. On our major yield loss, we start to get yield loss here quite early. It stays pretty much parallel, and then once we start getting to mid-August, we ran out of water. And the loss of yield there was in 25 because of the high radiation environment and the early planting. Again, we could have produced in this case about 104 tonnes per hectare, but we only delivered 78 tonnes per hectare. So that's just the practice of saying, if we had more water on here, we could have delivered closer to the blue line. Now those are big yields. Except that, we're up into the 680. In this case, about 670, 680 hundredweights. That's a big yield. And we've got lots of water. You can see the number of doses we put on. They're typically, in that case, 22 millimetres of water being applied. But the grower in this case just ran out of water. Not much more you can do about that.
So these are being planted the 1st of April to get those yields?
2025.
First.
6th, 7th of April, from that particular time. So emergence, you can see the green line going up. Emergence is basically about the 4th of May, so that would need to be planted a month earlier last year. So take a month off emergence date and you've got the planting.
And your calculation of potential yields, are you taking into account like fertility and soil health stuff there?
Yeah, that's all reflected in the canopy. The canopy capture is driving water use, and we've got a conservative calculation based on water use to convert it into fresh weight yield. If you had soil compaction, then soil compaction will change the growth rate of that canopy, and what will reflect it. If you have a canopy that ran out of nitrogen, then it's going to reflect it in terms of water use. If you had PCN, which is pruning, PCN, so root not nematode, or free living nematodes that are pruning roots, but the canopy manages to, then potentially we might not be able to predict yield as closely. So this is, you know, we've been doing this and calibrating against in-field digs, so 6 digs in each field, and taking the harvest yield and calibrating it. This works pretty closely. It's not perfect, it's a model, and you're only as good as the data you put in. But at the end of the day, if we could say your field has a degree of compaction, we measure with a penetrometer, we can actually adjust this in terms of what the potential yield would be. Some crops, it wouldn't be 100 tonnes, it would be 80, and we're only growing 60 tonnes. So yeah, it's possible to do that. And then, just to sort of bring you up and then talk about overwatering, this is a crop of Frito-Lay variety grown in Wisconsin, and this is 2007 data. And you can see the irrigations are 12mm applications on a centre pivot. There's a number of them, but you're drawn by the number of open triangles there, which is actually drainage. So when we look at that, the line colours changed a bit here. The blue and the green are up on the top graph, and you can't see much difference between the two. We actually, in this case, managed to maximise our potential water use because the soil was never ever wet. So 99% of the potential water use was met by what this farm did. However, we only produced 55 tonnes. However, we only produced 55 tonnes with 370 mils of irrigation, but a lot of drainage. Some of it was rain-induced, so there were 4 events when it just dumped down after irrigating. But most of the irrigations, as shown by probe data in the field, did cause drainage. Now, the key thing about this is we did it the following year, and then the following year we recommended some changes. We reduced the application of irrigation down to more like you might use it, thinking of 250 millimetres of water. The yield went up by nearly 10 tonnes per hectare. But the key thing is we actually reduced the internal defects because we weren't actually getting continual drainage through the soil. So that's the point when we sort of stop. And what I'm going to do is, instead of going on to scab control, I'm just going to show you what I've actually modelled in terms of water use for PEI mountain gem crop. Come out here. So, if we look at this, this is basically an unirrigated 2025 crop that I changed the planting date and emergence date of this crop this morning because I was told it was wrong yesterday, but not many people plant in April. So this was basically planted on the 16th of May and emerged on the end of the first week of June. So the canopy curve is there, unirrigated crop. You see the red line is the do not exceed, and the black line basically goes above it for a long period of time. The canopy is earlier, you can't really see that, but you'll see it in the next graph with the irrigated. And if we look at that and go down, you can see this is the actual water use and potential water use. There's a massive difference between the blue and the green. This crop isn't capable of using the water. And if we look at the potential yield here was around about, of that canopy, would have been around about 76 tonnes, and we produce around about 47. So we've lost effectively 40 tonnes of yield there. Okay, so that's what would happen if we had the capacity of irrigation to irrigate every, in this case I've said every 3 days with 15 millimetres. I've changed the scenario a bit from yesterday. And so we move to this, you can see all the irrigation events, they're 15 millimetre doses. We had quite wet, we had quite a bit of drainage post-planting and then basically pre-planting, and then during the season we had virtually no rainfall for that period. The black line is what we've scheduled the crop for. Each of the irrigations has gone on. If it wants an irrigation tomorrow, but we're really just finished, we can't put that water on that quickly. So there are some bigger gaps where we've actually said, no, you haven't got the capacity to irrigate. We look at that, then we actually see that the crop has been kept below its limiting SND for a large part of the season. How much water? 250 millimetres, 10 inches to grow that particular crop. There's the water use graph showing that only on a couple of days, and there's that 7 millimetre day, in the beginning of August or middle of August, and another day at the end of August when it was very high. But we've satisfied that demand, and what does that look like? If you could do it with Mountain Gem, you'd be somewhere near that where we could grow over 80 tonnes, so 650 hundredweights. Now, I did talk this with Brian yesterday, this morning, and when you look at this, this is probably the best of your yields, and it's taken about 10 inches of water. That seems to add up, but not every single yield has delivered 650 hundredweights per hectare. But if you look at the unirrigated, if you want to convert that, then the numbers that we've got here, the potential yield was over here, potential yield was 598, 600, and the model yield was 290. And that's pretty typical what Ryan was telling me today for an unirrigated Mountain Gem. Am I correct?
Yep.
Right ballpark? Yeah.
That would have been good for a lot of fields this year.
Yeah, yeah. So that's our scheduling approach, and it's all driven by how hot each individual day is, what the evapotranspiration demand is, because every single day the amount of water that the crop is used is calculated by this model. And if the water use is less than the potential, the yield goes down. And so we can't catch up, we can't apply water later in the season and gain that yield back. If you lose it, you've lost it for good. So that's an example of not irrigating and losing the best part of 300 hundredweights per hectare in terms of yield. Okay? Right. Ryan asked me about this. This is a clunky batch process Excel model. It's now been converted into a web platform whereby all this is done automatically. You get these graphs appear, you can toggle irrigation events in and out, you can put rainfall events in and so on. So that's going to be commercially released this year, and I think Ryan was talking about perhaps using it on some of the growers in PI, just as sort of a test approach. Right, so if I come out of that one and then finish off, have people got an interest in Common Scab?
Yes.
Yes. Okay, I'm going to sort of ask the question. Right, do you get much of that on your ware crops?
I'm trying not to.
Try not to, yeah. I mean, that's severely, what they call a rump and scab. The peeling losses on that tube on the left basically would be very severe. I mean, you'd be down 3-4 peels before you've lost the scab. So we're trying to produce blemish-free bars, and it's probably better to sort of describe it that you're looking for something a bit like this in terms of skin finish. I'll come back to that physiological score in a moment, but we're trying to grow blemish-free material for the packing. We don't want this. Now, how does irrigation work, and how do you apply it? I'm going to ask you this question because I've got my theories and practice. How does irrigation, when do you time it, and what do you do? So somebody who said scab's important, what do you do?
Generally try to start fairly early because we assume some of the infection occurs when the tubers are quite small.
Yep. And when would that be in terms of crop development?
Somewhere around maybe 35 to 40 days after planting.
Okay. It's a statement. So days after planting always confuse me in America and Canada. It's like, when so yeah.
First of June.
Yeah. Okay. Right. So we sort of got that, and that works really well with the UK because around about that early first week of June, we're thinking of doing the same thing with our climate. Very similar. You're later planting, we're earlier planting, but it takes longer to get emergence. So time-wise, we're in about the right thing. So the crucial thing here is basically why does irrigation work? The soil in the ridge where the tubers are doesn't matter what happens below or in the furrows or whatever. It's just where that ridge is. It needs to be wet and no more than moist in terms of dryness to prevent the build-up of pathogenic Streptomyces species. Now, there's a range of Streptomyces species. These are not fungi, and they are not bacteria, but they behave more like bacteria in terms of their response to soil environment. And the key thing I'm thinking about is changes in temperature and changes in water content. So if you get a soil that's dry, they drop. As soon as you start applying water and the soil is moist and conditions are conducive to growth, they will expand very rapidly in their population. So the key thing there is they will respond to changes. The reduction in those pathogen streptomyces is almost certainly due to relative shifts in other bacteria and fungal populations. But despite 5 years of work back in the early 2010, so 8, 9, 10, 11, 12, we didn't actually find that. Sometimes it was Pseudomonas, sometimes it was other antagonistic bacteria. Always something else went up when streptomyces, pathogenic streptomyces went down. But it wasn't consistent, so that is soil dependent. What controls it is two things. One is those antagonists can either produce antibiotics, and so streptomyces will be killed by the production of antibiotics by other species on the surface of the tuber, or the tuber's only so big, it's just a competition for the carbon, the sugar that leaks out of that tuber. There's only so much space on that tuber. As it gets bigger and bigger and bigger, then there's more carbon leaking out because of the surface area, but gradually that carbon stops, the tuber forms a semi-set skin, and it stops. So therefore, basically everything disappears. And if you looked at streptomyces scabiei populations at the end of the season, on tubers you'd find nothing, or you couldn't detect nothing. Why? It's because there's nothing on the tuber worth having. It's not leaking, the tuber's now sealed itself up. But there's a lot of leakage in this early point of the season. So the key thing is, it's this crucial period is when 1 to 3 weeks after tuber initiation, rather than saying days after planting, this would be days after emergence. This would be around about 3 to 5 weeks after emergence of the crop. We need to be maintaining the soil wet to moist and no drier than moist, but we don't want to overwater because we get cracking. I've shown you the pictures of that. We get lenticel eruption and we get potentially more blackleg if there's blackleg coming in from the field from aerosols or on the seed. So, 2 graphs showing the build-up of Thaxstolin producing streptomyces in terms of the higher the number, the more potential pathogenicity, the more disease. So with Meris piper, our most susceptible variety, far more susceptible than Russet Burbank to scab. Basically, if we plot this pattern, this is weeks after when the tubers initially are now twice the diameter of the attachment stolon, so it's weeks after tuber initiation. We watch 1 week, 2 weeks, we only start to see an increase in pathogens after 2 weeks. That's because there's nothing being exuded on the surface of that tuber that anything wants to live on. But the key thing is, if we keep the soil dry between weeks 2 and 4, suddenly we see that massive increase in terms of pathogens. That high pathogen, it goes from basically it multiplies by a level of 10,000-fold. That's a massive change in population. We get a lot of disease at the top one with unirrigated Meris piper. As we irrigate and keep the soil moist, then basically we reduce the level of pathogens and we get less disease. And if we keep the soil at field capacity, we effectively drown it, then we get probably no pathogens observable. Now, detection is a limit, about 100 copies per gram of tissue is about our limit at this stage. So it doesn't mean to say they aren't there, it just means we've suppressed them almost completely. We get no disease when we keep the soil at field capacity. In other words, there's no scab. A basically resistant variety, not completely resistant, but one that is on a scale of 1 to 9 is an 8 out of 9, and this is a 1 out of 9. And basically, we get the same response, it's just damped down. So instead of getting 10,000-fold, our irrigated crops will get basically a 1,000-fold difference change. So we're still seeing it, but we can actually now reduce it. So the answer about this is, Vale Sovereign, we can irrigate basically with a drier soil profile because it doesn't get as much pathogens, it doesn't develop the disease. But the key thing is that varieties differ in their response to irrigation in how many pathogens they will produce under dry conditions. So we control it by keeping the soil moist to wet and not allowing it to dry out. So that's a sort of summary of it. What do we do practically? In sensitive varieties, so I've used Meris piper, or varieties that get scab and you're concerned about packing, if the soil is dry, then the first irrigation will need to be when the first plants are beginning to initiate tubers. But there's no pathogens. Why would we irrigate them? That's because we want the ridge wet at the point when the pathogens want to start developing. That sort of 1 to 2 weeks after tube initiation is the real key stage. So we've got to get our ridge wet, not from the point of when the tubers are initiating, but in the next week to 10 days. We've got to make sure that ridge is wet, and it's got to continue irrigating for about, in the next slide, about 3 to 4 weeks. I'll explain that a bit more. With less sensitive varieties, the Vale Sovereign or the varieties that don't really get scab, we can afford to start a week later because we never get that level of severity that we would do on a very sensitive variety. If you irrigate and the ridge doesn't wet up, then you're trying to wet the whole ridge. You've got to do a repeat application. Basically, if you wet a ridge, the ideal scenario would be is to wet a ridge, basically come back a day later and wet it again, then it would wet up. So it's like a repeat application. Now, pre-irrigation, these capped hydrophobic, where the soils have gone dry, your planting to emergence is pretty rapid. In the UK, we can have 6, 7, 8 weeks between planting and emergence, and our soils will cap, they'll become hydrophobic, water will shed off them, and often we need to pre-irrigate to get the ridge wet, and then we need to do it again. Okay, so what does that mean? We talked about soil moisture deficits, and what this is the ridges are literally 8 inches deep where you're growing your tubers. This is the maximum amount of water we can empty our new bucket. The bucket is now only 20 centimetres deep, so we're dealing with just the ridge. On a sandy soil, for a sensitive variety, would be 10 millimetres. On a sandy loam soil, your type of soil, we'd be running a 15 mil deficit. Clay loam, pretty much similar, and the silt loam, the most water-intensive soil, would run even drier. But that's based on the most sensitive variety. So if we then go to this table here, this is a result of sort of 7 years of work. A range of varieties, not very easy to see, but Maris Piper, Maris Peer. Maris Peer is a creamer. Maris Piper is a main crop variety, very susceptible to scab, and basically we need to maintain the soil moisture deficit on our sand less than 10 millimetres. So this is just duplicating the previous slide. If we move to the resistant phase, nothing's resistant, nothing's a 9, they're 8 out of 9, we can run the deficit almost twice as big. So this basically means we're keeping the bucket less full with our resistant varieties than we would be with that. Now, I've not got any information on Mountain Gem where that fits in if you're growing it for a table market, but some of your table varieties would have different levels of resistance in terms of red, amber, yellow and green in terms of it. So this is the result of what we've done. It's produced this table for different varieties, and if we don't know it, we would put the variety somewhere in the groups 2 or 3 in terms of its resistance and how we would irrigate it. So that irrigation scheduling program that I showed you has common scab built in, but in the early part of the season from tube initiation, we're trying to maintain these very low soil moisture deficits, keep the soil moist to basically prevent scab. I talked about this many, many years ago in the Pacific Northwest, and they laughed at irrigation being able to control scab. Does it work in PEI?
Yep.
Yeah, it does. You've got similar, different species and strains of Streptomyces, but if you've got certain ones, they don't respond to watering, but the majority you've got on PEI from surveys certainly do.
What's the number after the varieties there?
That is, Ryan mentioned NIAB. NIAB is an agricultural institute that basically produced a ranking on a scale of 1 to 9, 1 being highly sensitive to scab or to blight or to PCN or root knot nematode, and 9 being fully resistant. So what you've got here is they're very, very sensitive to common scab in the red, and over here you've got 2 varieties that have got scales of 8. Out of all of these, Perline is a creamer, a very, very productive salad variety, and basically that has a resistant rating of pretty much 8.9. You don't get scab on Perline at all. So that.
You have some stuff that's, you have 6s in all 3 columns.
So which is right? So this has been done on lots of multiple trials. This is either unirrigated or irrigated at NIAB with very limited comparisons, or it's data from breeders who've told it this is our resistance. But what we tried to do is say the NIAB ranking, mainly, as you said, it could be in groups 2, 3 or 4 with the same resistance ranking. So if I hadn't put that on there, what I trust is where the columns actually line up. That's not to say Safari can't be more like a group 3, under certain circumstances. But a Silvana, there's most of them at 6, but a Butte basically may have a high sensitivity, but actually it doesn't show it when we're in the field. So sort of ignore that in terms of the resistance ranking, because it's a bit confusing. I trust my own data rather than some quite simple comparisons that I have done. They're often based on only one trial in 1 year. Okay. Right, that's irrigation. Questions, and irrigation topic is still open. Anything else this is in the quality section. Why don't we just water the crop to basically protect it from scab? This is what happens, which is the same as the bruising story. These are 2 Maris Piper tubers that were kept at field capacity for 3 weeks after they initiated, and literally the quantity of water available to them has made the tubers burst. These burst at about 20mm diameter, so big marble size. They burst then, they split, because the tuber at that stage doesn't have a skin that can support that internal pressure, so they split. So this has happened at the end of the season, this has happened very early. Also what we tend to get is lenticel eruption. Tubers basically are lacking oxygen in the soil. When water replaces that oxygen, they will then be open, they're a breathing pore, there's your pathogen entry point to the particular crop. Paddy scab also gains a root in that way. And the other one is if we look at this, just a different form of cracking here, sort of a more netting type cracking with Veil Sovereign. And if we look at blackleg, what we do know is blackleg here, these are trying to mimic scab control regimes on a sensitive variety with a known blackleg infection in the field. If we don't irrigate the crop, we still get blackleg. If we irrigate the crop for a long period of time, for around about 4 weeks, then we end up with a red line. And we follow that through the whole season, so we keep the soil moist to wet from the middle of June right through to the end of August. We end up with more blackleg. If we dry the soil out a little bit, in other words, we allow a 2-week delay, as soon as we've finished scab control, we stop watering, then the green line results, less blackleg. And if we allow a 4-week delay, clearly the plant's a bit under stress, we end up with less blackleg. So managing scab control with a blackleg incidence in a crop is really crucial. But once we've started irrigating, we've developed the disease during that early period. It's very difficult to control that. But we've got to manage it. Switching off irrigation is any way we control the rampant development, like it shows in this particular crop here, where we end up with inoculated tubers there, with irrigated, and suddenly we've got more than 70% of the tubers of plants with blackleg.
Any questions before we wrap up, folks? I know we're eating into your lunch hour a little bit.
I have a quick question. How do you measure the soil moisture and the evaporation? Like, what's the best tool or platform?
Everything I've done to the point of tuber quality is all about using evaporation data from meteorological data. Okay. So we capture it. The model example I used a combination of actual data from the weather station provided by the PEI board, and then basically I combine that with a more generic, MeteorBlue is a Swiss firm that allows me to put a pin in the field and generate the evaporation component for that field for that particular year. We then capture data from satellites to drive the canopy of the growth. That allows us to say how much water that crop will use, and then the sophisticated part of the modelling does and say the practice you do with irrigation will measure that deficit. It doesn't measure it, it predicts it. So it's a model prediction. So it works on 19,000 fields with very little comebacks and whatever. It's not always right, but with scab control, we are dealing with 20 centimetres of soil, and it's really difficult to predict water entry into a ridge with different soils and with different canopies. So that's when measurement would be really, really good. And so there are lots of tools, but I would suggest for scab control, when we've got, we go right back to the beginning, we are measuring with devices like, okay, these on here. So what we have got here is, most common would be the ones in the middle. So that's an EnviroScan, okay, which is a capacitance type probe which measures water by measuring the ability of the soil to conduct electricity. And the dielectric constant of air is basically 80, so air is a really good insulator. soil is around, sorry, air is, on a relative scale of insulation is 0, soil is about 5, and water is about 80. So water is really important. So that measures the ability to conduct a voltage between two measurement points in that gold-coloured symbol there. That will allow you to measure directly the soil water content, which allows you to calculate when you need to irrigate. So scheduling with a probe is really useful when you're dealing with something that is a really, really shallow area that you're trying to get neither too wet nor too good. If we get it a little bit wrong in the modelling, the bucket size is a little bit out or it's a little bit under, it doesn't make a lot of difference doing it, but with scab control it's important that we probably measure. Now, the other one is to measure, actually it applies on most soils. If you can go out in the field and you go down to basically the middle part of your ridge, not the top, which is often the driest, not the bottom where it's, go to the middle part, just above the seed piece, and you can ball a soil and it will hold together. That soil is moist enough to prevent scab. Okay, that's a really simple technique, but it actually does work. You've got to walk a few places around the field to do that, but that's what you're aiming for. Then you get a sort of view, we irrigated and our soil is now too wet, or it's too dry, you can squeeze water out of it, it's too wet, or it won't ball together. We need to really be in this field yesterday. That's actually one of the best ways of doing it. Sadly, it's not very scientific, but it really, yeah.
Any tips before you leave to avoid scab other than water, like pH, sulfur, etc.?
Yeah, there's been a few papers in the UK. George Lazarovitz did quite a lot of work on everything under the sun in terms of growing things with sulfur, with cow manure, pig manure, calcium, various soil sterilants and things like that. Soil sterilants work because they kill everything. The problem is streptomyces bounces back really, really quickly. So if you have fumigated soils for verticillium ahead of potatoes, often next year you'll find that common scab comes in really, really rampantly. In terms of nutrition, the work on sulfur that's been done elsewhere, you look at all the papers and you combine them, it isn't convincing. Sulfur, if it changes pH, the general rule, if you can push pH below 5.8, then the organism won't actually develop. The organisms we're talking about here. But if you've got Streptomyces acidiscabies, it functions in acidic soil. You just suddenly create a problem for yourself because now you've pushed the pH into something it really likes. So 5.8, 5.7 tend to be the bottom end. You can get below that, but then you've got issues with nutrient uptake at that end. So scab likes stuff more acidic, or doesn't like stuff more acidic. It's difficult to get that. 6.5 is the optimal. Going the other way, pH 8.5, well, there's a lot of very freely available calcium there. Is it the calcium controlling disease? Because I've seen pH 8.5 soils come out blemish free. And the pH there, you go, that isn't the story, but it's the calcium. Calcium's been implicated in that it can make the tuber more resistant to damage. So what you tend to get is cells more structurally sound, but actually doesn't have any effect on scab whatsoever. So sulfur is the main one. I was talking to somebody about gypsum at the break. Gypsum's an interesting one, that we use gypsum by chance, in that we were doing some work with calcium sulfate, and we were concerned that the sulfate was changing pH. So we then basically put sulfur on to balance that. In order to put a neutral component, we put gypsum in, and gypsum had a far greater effect on common scab in reducing it than any other thing we tried. Almost, not as much as water. And I think that is doing, it's not due to nutritional uptake by the plant, it's to do with soil conditioning. So what you're getting is you want to maintain that film of water around the tubers. That's easier if you can get that really good, smooth contact. A bit like a Malteser. Do you have Maltesers? Yeah. So you're trying to get that coating around the tuber of moist soil. That's the environment that basically keeps all the good antagonists and keeps out the guys by just killing them or swamping them off the tuber. So we're thinking about keeping that moist to wet. If soil conditions are cloddy, you're not going to do it. If soil conditions are really fine, you stand a good chance of actually achieving scab control. But nutritionally, yes, I can give you experiments left, right and centre, but if you look at the overall evidence, it's not there.
Thank you.
We are seeing a trend in some work we've done the last few years with Minuet product, like the in-furrow biopesticide is in-furrow bacteria, and the trend seems to show that, you know, not every year, but there does seem to be some association with lowering scab with it as well.
Maxim in Canada you use?
What?
Maxim?
No.
I don't even know. Maxim is in the UK is flutonil, and
Right.
flutonil has an effect.
Okay.
And so that's a seed treatment, and it's clearly it's very significant. But it's adding to water control. Water control is still the main function.
Anything else? All right. Thank you so
Good.
much, Mark.
No, thank
Really
you for-
appreciate it. Mark came a long way at a very busy time. He should have said no to me, but he didn't.
I could have been in
And,
South Africa last weekend riding a race with my buddies in the village, but I said no, I've committed to Ryan.
Committed to come to Canada in March and see snow. Anyway,
He said he wouldn't get you guys to be here in July when I wanted to come for the
yeah.
summer. So he said, right, it's important we have people to listen to you talk. Let's come, and I'm fine. But it's
So
great to come.
I just told him now he has to bring some growers over for a study tour in July or August, and we'll take him around to some farms and see some actual potatoes. So